Hey everybody, we're gonna get started in just a minute here talking about doing some vertical asymptotes and holes. We'll learn the term in a minute of discontinuities in rational functions. This is the second of three sets of notes I'm going to be looking at for graphing rational functions. The last one, if you haven't already gotten a chance to look at it, it's already up. It's on simplifying rational functions or expressions, usually by factoring. So we're going to use that skill here today, and then we're going to build off of those excluded values we were looking at last time, and really differentiate between what types of excluded values we've got. All right, let's give it another minute or so before we really get going. It is 4:28. This is for all of my class periods. All right, well, let's do this. Here we go. A rational function, f of x, is the quotient of two polynomial functions, p of x, q of x. Okay, this would be one polynomial up here. In the case there, our p of x is x squared minus 1. Over here it's just the number 3. And q of x is the denominator polynomial. In this case it's x plus 2 or x squared plus 4. The big idea here is that the bottom polynomial, which is in this case q of x, cannot equal 0, okay, because you cannot divide by 0. All right. Now, the main and first thing we're going to look at is vertical asymptote. A vertical asymptote is a vertical line that the graph approaches but never intersects. Think of it kind of like a fence versus an electrified fence. Okay, you could touch a regular fence. You can go all right up to it and touch it. An electrified fence, well, you can get up really, really close to it, but you probably don't want to actually touch it. And you can get infinitely close to it, theoretically. As long as you don't touch it, you're not going to get electrocuted. Okay, so in this one here, the line x equals 0. Okay, remember, if it's x equals a number, that's the equation for a vertical line. Y equals a number, that's the equation for a horizontal line. We're not talking about horizontal today. We'll do that in another video. Okay, x equals 0 would be a vertical line right here. Now it's really hard to see. I'm going to change to another color here, but this graph does have a nice happy vertical dashed line here, and as you can see, these curved bits here, sometimes call them L's because they, I don't know, vaguely resemble the letter L, but they get infinitely close over here, and this one's getting infinitely close over here, but it's never going to touch and it's never going to cross. Okay, so what we're saying here is for this function, okay, 1 over x, if you plugged in 0, you would end up with 1 over 0. If you put it in your calculator, you would end up with a domain error. Okay, you're not allowed to do that, not allowed to divide by 0. Okay, that's basically the gist of it. For right now, I'm not really concerning ourselves with the exact look of these L shapes. Okay, we'll worry about that once we introduce horizontal asymptotes in another video. So for all of our examples here, I'm either going to have them shown for you, or I'll just sketch them in, and then you won't have to worry about anything else until later. Okay. All right, so as x approaches 0 from the negative side, okay, from the negative side, that's going this way, okay? As x approaches 0, okay, so we're here, here's the graph here. It's going down, 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 down. It's getting faster and faster, faster, and now it's like just racing towards the bottom until we get there. So down here, that's negative infinity. Okay. As x approaches 0 from the positive side, that's from the right going left. So you look at this L, and it's going up, 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 up. Suddenly it's going really, really fast, but it's going up ad infinitum. It's going up to positive infinity. Okay. So there we go. As x approaches 0 from the negative side, it's approaching negative infinity, and as it approaches 0 from the positive side, from the right, it approaches positive infinity. All right, here we go. Let f be a rational function in that format, the numerator p of x, denominator q of x, and they have no common factors. Okay, everything that happened in my previous video in this trio that's going to be coming out, we're not worrying about the part about canceling anything out or anything. Okay, so anytime q of x, that's the bottom, equals 0, those are your vertical asymptotes. Okay, 0 is still important for the top. Okay, if the top p of x happens to equal 0, well, that means that you end up with something like 0 over whatever q of x happens to be. Okay, so in other words, you have, well, an x-intercept. Okay, you have the ordered pair something, comma, 0. All right, and any fraction doesn't matter. I mean, you have 0 over 5, 0 over negative 12. All of those are just different ways to write 0. Those are your x-intercepts. Okay, that's where the top happens to be 0. All right, here we go. Find the vertical asymptotes for this function. Okay, now these are our two. Q of x is this guy. P of x is this guy. Remember, an asymptote exists where the graph can't exist. And the only rule we're worried about right now is that you're not allowed to divide by 0. Dividing by 0 only happens if the bottom is 0. So we only care for right now about that bottom piece. So to say q of x equals 0, we'll do x minus 5 is 0. And solve it real quick. Add 5, x equals 5. That is our vertical asymptote, and you can see it drawn in right here at x equals 5. Now for the top piece, p of x, we will go ahead and solve that one for 0. X plus 3 equals 0. Subtract 3 from either side of your equation. And this is going to be our x-intercept. Okay, negative 3. You can say it as an ordered pair, negative 3 comma 0. But you can see right here that dot has been provided. All right, and that's the gist of it, really, for right now. Is we're talking about vertical asymptotes. Okay, now this entire idea of there being these gaps in the graph, these are all called discontinuity. All right, a discontinuity is any place where the graph doesn't exist. Okay, or you could say stops in somewhere in the middle. Alrighty. And we're concerned with two types: discontinuity with no extra adjective added, and then what is called a removable discontinuity. Okay, let's jump over to 11 here. I know I skipped over that to talk about these two guys. If you remember the rules here, x squared minus 4, that is an instance of difference of squares. That's your a plus b, a minus b format. Okay, so we've got x plus 2 times x minus 2. Alrighty. And then for the bottom, you're looking for two numbers that add to get the number here, which is a 1, and here to get negative 2. Okay, now to get 2 or a negative 2, it's going to be a 1 or a 2, a 1 times 2. One of them is going to be negative, one is going to be positive. If you're not sure which, go ahead and write down both possibilities. You're either looking at 1 minus 2 or 2 minus 1. One of those gives you 1 as the answer, because that's the number in front here, 1x, positive. And that's this right here, 2 minus 1. So 2 will be positive, and it'll be an x minus 1. And now we can go ahead and cross out the common factors for the top and the bottom. You'll be left with the new x minus 2 over x minus 1. And it says there, remember to include excluded values. Well, here we go. X cannot equal, okay, well, this one here is 1. 1 minus 1 gives you 0. But we have to include this one as well. Negative 2 plus 2 gives you 0. So those are our two excluded values. Alrighty. So vertical asymptotes, it's what we've already talked about here. That is the non-removable one. It's the one that, well, didn't get removed. All right, we solved this, plus 1 plus 1. X equals 1 is the vertical asymptote for this graph. Okay. Now the next term is called a hole. And these are called the removable discontinuities. You see this part right here, we canceled out earlier the x plus 2's. And that's where the negative 2 came in. Okay? Thing is, if you plugged in negative 2, you wouldn't just get a number over 0. You end up with 0 over 0, because it makes both the top and the bottom become 0 in the original. Okay? So if f of negative 2 is undefined, so there is a hole in the graph at x equals negative 2. Okay, a hole is a removable discontinuity, and an asymptote is not removable. And take a look. Here is our vertical asymptote at x equals 1. There it is. We're approaching that, and we're approaching that. Here, this L was drawn in, and just right here, well, it's a hole at -2. If you remember your graphing, particularly for like a number line, an open circle means you get infinitely close to that spot, but not including that spot. So -2 is undefined for this, but everything around it just goes business as usual. But it's not an asymptote, it is a hole that's just been removed. All right, so let's just do one or two of these here, and we'll be all set. Okay, down here, this is a difference of squares, so that'll be x plus 6 times x minus 6. And the part that's going to cancel out are the x plus 6's. Okay, the asymptote comes from this guy right here. X equals positive 6. The whole is going to come from this one here that canceled out. X equals -6. Now remember, the x-intercept is whatever would cause the top to be 0, which would be -6, but we already said that that is our whole. Okay, this simplifies to 1 over x minus 6. And, well, think about it. It is 1 itself. There's no variable in the top anymore. It's just 1. Is that ever going to equal 0? No, it's 1 on top. So there is no x-intercept for this particular one. Okay, let's go ahead and do g of x. The top is, once again, a difference of squares. We have x plus 5 and x minus 5. The bottom two numbers, multiply them to get 5 and add them to get 6. That's going to be 5 and 1. And we look at what we can cross out. That's the x plus 5's. The ones that got crossed out, the x plus 5's, that's our removable one. That's going to give us our whole. This one right here, the x plus 1, is going to give us the asymptote. So -1 plus 1 gives you 0. That's our vertical asymptote. Whole, that's the bottom here. -5 plus 5 will give you 0. And now we can look at the top here, because this piece was not crossed out, and putting 5 in, okay, is not going to do anything significant to the bottom. Okay, there's no issues with plugging in 5. So you can say the x-intercept, it's 5. If you want to do an ordered pair, you can call it 5, 0. And, well, everything else here is basically just more examples of that same thing. Sometimes you'll have a hole, sometimes you won't. Sometimes you'll have an x-intercept, sometimes you won't. But that's basically it. The next video, which I'm going to do a live stream tomorrow, we'll talk about horizontal asymptotes and how to find those, and then we can actually really get into, graphing these. But, well, thanks you very much. If you need any questions about the rest of these, I'll be doing my conference on Schoology this evening.